Hi, my name is Tan. Today I'll talk about totally geodesic surfaces in hyperbolic non-complements. This is joint work with Rebecca Palmer. Let me first define totally geodesic surface. Let M be a finite volume hyperbolic 3 manifold. A totally geodesic surface in M is a finite area surface, such that any geodesic on N is a geodesic in in group theoretic terms, these are surfaces arise at quotient of hyperplane in H3 by finite co-area functions. Here are some examples of totally geodesic surfaces. First, one can take the twist knot complement. The dotted surface in the diagram on the left represent a totally geodesic sphere. One can also consider the three-strand balance crescent knot in the diagram on the right. The dotted surface here represent a totally geodesic cipher surface. Our motivation for studying totally geodesic surface comes from the recent work by Barter, Fisher, Miller, Stover, which say that if M is a hyperbolic 3 manifold that contains infinitely many totally geodesic surfaces, then M must be arithmetic. The natural question following this work is to find example of hyperbolic 3 manifold that contains exactly k totally geodesic surfaces for any integer k. Prior to our work, the answer for this question is only known when k equal to 0. So we have the following example due to Reed and Caligari. So the Weeks manifold, which is obtained from doing name filling on the y-hat link and the knot 820, both do not contain any totally geodesic surfaces. Our main result concern the complement of the twist knot Kj denoted as Mj. So this is the fully geodesic three-puncture sphere N in Mj. And our main results say that this three-puncture sphere N is a unique totally geodesic surface in Mj for any R prime J. Using some covering trick, we also construct example of hyperbolic 3 manifold with exactly k totally geodesic surfaces for any positive integer. Here's the strategy for our proof. First, we note that these manifold Mj do not contain any closed surfaces, and this is a result due to Reed. Second, what we do to rule out cup surfaces is to classify the ways a totally geodesic surface can intersect the torus neighborhood of the knot using the following set of constraints. First, the geometric constraint will say that the intersection of any two totally geodesic surfaces is a union of closed and cups-to-cups geodesic. And second is an arithmetic constraint, will say that the traces of the function subgroup corresponding to any totally geodesic surface in Mj are all integers. Together, these constraints give us the boundary slope constraint, which say that totally geodesic surfaces in Mj must have two boundary slope, 1/0 and -2, with respect to the standard, meridian, and longitude for a knot complement. And finally, by playing these constraints off each other, we were able to conclude that the three-puncture sphere N is the unique totally geodesic surface in Mj. And as a conclusion, let me describe some of the work in progress. So by modifying the previous strategy, we were able to determine that the twist knot, we were able to determine that the knot 74 and the knot 935 in the Raphson knot table contains a unique totally geodesic surface. And by expanding on an obstruction to the existing totally geodesic surfaces in a fiber knot complement by Caligari to the non-fiber case, we also determined that there are 45 knots among the 79 hyperbolic knots with at most 9 crossings. Contains no totally geodesic surface in this complement. That's all I have to say. Thank you for your attention.